you, when I put up this warm-up problem, was like, what? Like limits? We haven't done that in so long. That's fine. Okay. I'll tell you why we're doing it. Just be patient. Okay, so what is the issue with trying to evaluate this limit? We get 0 over 0, right? Okay. And flash back to Unit 1. If you had 0 over 0, that meant you could do something algebraically. All right, what algebraically can we do to this limit? Okay, well that's really not helpful yet. Okay, so we can factor that, whoops, we can factor that numerator. The x plus 1's cancel. Now can we plug in negative 1?
Yeah.
And when we plug in negative 1, what's our limit? Okay. What if I told you that that's not the only way that we can do this problem? The other way is not more difficult. Oh, the other way, maybe it would involve derivatives, since we're talking about applications of derivatives in Unit 3. Just listen to yourself. Okay. So, L'Hopital is how you say his name, was a French guy. He came up with a rule for when we have indeterminate limits, specifically 0 over 0 or infinity over infinity. Write it down, then we'll chat. Write it down, then we'll chat. Okay, so some of you are panicking that you're going to have to do the quotient rule. Do you have to do the quotient rule? Well, if it's indeterminate like that, the whole rule will work. It's just like it's possible to do it and we get if it were like 1 over 0, that's not but
in other words, nobody could tell me I'm wrong.
okay, so if we have 0 over 0 or infinity over infinity, notice how this has to be a fraction, okay? And if our fraction limit gives us either one of these indeterminate forms, then we can take the derivative of the numerator separately from the derivative of the denominator, and then take the limit again. And if that's indeterminate, then we can do it again. But we'll get there if we need to. Okay? But it actually saves you from doing some algebra. Instead of having to factor and cancel out terms and then evaluate our limit, we can just apply L'Hopital's rule, derivative of the numerator, derivative of the denominator. Try again. Okay? Please understand that this is not how you take the derivative of a quotient. Okay? L'Hopital's rule works with a fraction, but we take our derivatives separately. Okay? Now, 0 over 0 and positive or negative, infinity over infinity, are going to be the two indeterminate forms that you see the most often. However, there are other indeterminate forms.
Oh.
Just write them down, and we're not going to discuss them. 0 to the 0 power is indeterminate. 1 to the infinity is indeterminate. We're not going to work with those in this class. We'll save those for BC. Okay? Infinity minus infinity is indeterminate. Because infinity is not an actual number, it's a concept, and some infinities could be bigger than other infinities. You could be approaching infinity quicker or slower, and so taking the difference. Okay? 0 times infinity we will look at today. And then we will not talk about infinity to the 0. That's another one we'll save for BC or Calc 2, whatever you take. All right? But if, like I said, we're not going to talk about these. But if they were to be this indeterminate form, we would have to rewrite the limit to where it could be a fraction so that we could use L'Hopital's rule. We would have to rewrite it to be 0 over 0 or infinity over infinity. Okay? But let's just start by using L'Hopital's rule. Okay? So I want to go back to our warm-up problem. Rewrite it for me. Okay? If your limit is indeterminate, I want to see that you identified it that way. So do you see how I actually wrote 0 over 0? Okay? That's my sign from you, or that's your sign to me, I guess, that you're going to use L'Hopital's rule. Okay? It's 0 over 0. It's indeterminate. So we're going to apply L'Hopital's rule. The derivative of our numerator, 4x. The derivative of our denominator is 1. Now, when we plug in -1, we get -4. Hey, is that what we got with algebra? Yeah. Good. Which one was quicker? L'Hopital's rule was quicker. Okay. Do I hear whining?
No. Yes, I know.
No? You're like excited? Okay, so write this one down. No, we're never done.
0 is 1, right?
Yes, e to the 0 is 1. So when we try to evaluate this limit, we get
0 over 0.
0 over 0. That is an indeterminate form. Let's apply L'Hopital's rule. Colby, what is the derivative of e to the 3x minus 1?
It is 3e to the 3x.
Okay, the derivative of x is 1. So now when we try direct substitution, when we plug in 0, we get 3 times 3 times 1 over 1. Pretty slick, right?
No, sometimes like a decimal every time. Well, clearly the problem's here. Oh yeah, there it is. Emma. There it is.
Look.
You're saying.
Just write it down. What is the natural log of infinity? Well, that doesn't really make sense. Let's think about the natural log graph. The natural log graph looks like this. As we approach infinity, where's the natural log going? Okay. The square root graph looks like this. As we go towards infinity, where does the square root go? Ah, okay. So sometimes we got to think about what that graph looks like. This is why it's indeterminate, because we cannot say that it is. Okay. Infinity is not a value. Infinity is a concept. Okay? So we have an indeterminate form, which means we can use L'Hopital's rule. Ooh, what's the derivative of the natural log? Okay. 2 radical x is like 2x to the 1/2. So it becomes x to the negative 1/2. I would encourage you to simplify before you try to evaluate the limit again. I have 1 over x divided by 1 over radical x. Right?
Yeah.
Okay, so when we try to simplify this, okay, so we have 1 over x times x to the 1/2, right? So ultimately we have 1 over x to the 1/2 power. Ask a question if you have it.
I do have a question.
Okay. 1 over x, I wrote it. So this is like, you can think of this 2 different ways. You can think of me moving this to the numerator as x to the 1/2 power, because when you move it across the fraction bar, it becomes positive. Or you can think about this being 1 over x to the 1/2, and when we divide, we multiply by the reciprocal. Okay? Now I have x to the 1/2 over x to the first, and when we divide, we subtract our fractions, or subtract our exponents. Now, what happens to our denominator towards infinity? It goes to where, Jordan? You just whispered something.
I don't know if it's right.
That's okay.
I'm wrong all the time. I said like 2, and it was like not 2.
It's going to infinity. And so if we have 1 over going towards infinity, then that fraction is approaching
0.
Your denominator is getting bigger and bigger and bigger and bigger. This, the square root of x, towards infinity is going towards infinity. If you have a fraction where your denominator is getting bigger and bigger and bigger and bigger and bigger and bigger and bigger, your fraction as a whole is getting smaller and smaller and smaller and smaller and smaller. This is one of our properties that we have. That's something that we talked about in Unit 1. If our denominator is going towards infinity, that means our fraction is getting smaller. I'm just waiting for it to be quiet, but it could take a while. Thank you. If we think about the numerator only, x squared, what happens towards negative infinity? If we think about e to the negative x, that's exponential decay. What's happening towards negative infinity? Exponential decay looks like this. So infinity. It's okay. Infinity over infinity is indeterminate. If we have our indeterminate form, we can take the derivative of the numerator over the derivative of the denominator. So now what happens when we try to evaluate the limit? Let's see. Towards negative infinity. What's happening to 2x? What about negative e to the negative x? Hey, that's okay. Because all that means is we have indeterminate form again, so we do it again. If it's indeterminate, use L'Hopital's rule. So now we have 2 over e to the negative x. You already told me that e to the negative x, as we approach negative infinity, would go towards infinity. So we have 2 over approaching infinity, which would be 0. So if e to the negative x looks like this, then negative e to the negative x flips over the x-axis. Yes. Because as we approach negative infinity, this guy is going to go towards infinity. So we have 2 over approaching infinity. So as our denominator gets really, 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 really big, our fraction as a whole gets really, 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 really small. Do you see what I mean by that? Okay. Yes?
For the top right thing that you wrote, how would the denominator for the negative? Because if you plug the, oh wait, never mind.
Okay. I know some of you like pushed limits to the very back of your brain, and right now, some of you are struggling to pull them forward because you really wanted to forget all about limits. Okay. But we will have them on our final both this semester and next semester, so it's kind of nice to come back to them a little bit. Oh, don't give me that look. You love it. Yeah. Okay, couple more examples. Now, if hold on. What if I gave you something like that? Can I use L'Hopital's rule on this?
No.
Turner, why not?
Because it's
It's not indeterminate. This is 1 over 0. Okay, which means that there is something happening there to where we can't actually evaluate the limit. Specifically, what is happening here at 6? We have a vertical asymptote at x equals 6. So we would have to figure out what's happening on the right side and left side of x equals 6. What happens is the right and left are approaching 2 different infinite values. So this limit wouldn't exist. Okay? We can only use L'Hopital's rule if we get the 0 over 0 or infinity over infinity. Now, we can't apply L'Hopital's rule directly when we have one of those. We have to tweak it. Okay, and we're going to look at an example like that. What?
And make it like 0 over 0?
Yes. Okay, so let's go to one of those. Towards infinity. We just drew e to the negative x. Towards infinity, where is it going? Let me draw it again. Radical x. Towards infinity, where is it going? Okay. 0 times infinity is the other indeterminate form you will find in your homework tonight. Okay, however, this is not a fraction, so we can't apply L'Hopital's rule, but it is indeterminate. So let's rewrite it so that we could maybe use L'Hopital's rule. Okay? How could I take this, e to the negative x radical x, and write it as a fraction? Okay, so we can take e to the negative x and make it a positive e to the x in the denominator, excuse me. Now we have the official indeterminate form of L'Hopital's rule, infinity over infinity, or one of them, right? Now we can apply L'Hopital's rule to this guy. Okay? Oh man.
Why is that video?
Square root graph looks like this. So towards infinity, we approach infinity. E to the x graph looks like this. So towards infinity, we're going towards infinity. Okay. Well, we could say anything times 0 is 0, or we could say anything times infinity is infinity. We can't like which rule wins. But infinity, and see, here's the problem. Infinity isn't an actual number; it's a concept. Okay, Yes.
So even though
So, like,
0 times infinity is indeterminate, you have to show that it's either 0 over 0 or infinity over infinity.
Yes, you have to rewrite it so that you can apply. Because L'Hopital's rule only works if you have a fraction. So you have to force it to be a fraction. Okay? So now we can apply it. 1/2 x to the negative 1/2 in our numerator. And, woohoo, e to the x in our denominator. What did I tell you? If you can simplify, you better simplify before you try to evaluate anything. Otherwise, you're going to get stuck in a rabbit hole that you don't want to be in. Okay? So, if I want to simplify this, yes, it's 1 over 2 radical x e to the x. The 2 gets to be in the denominator. X to the negative 1/2. Let's put that in the denominator as a positive exponent. Okay? Now, we've already thought about these. E to the x goes to infinity. Radical x goes to... So my whole denominator is going to... So my fraction goes to 0. We have one more example that will not equal 0.
Yay.
I'll tell you that right now.
Zero. That's gonna be an issue.
See, the problem is I can put letters into math when it goes down.
Okay. Towards infinity, what happens to x? Times sine of 1 over x. Well, what happens to 1 over x towards infinity? It goes to 0. So the sine of 0 would be 0.
So if you look at this far away, that's
If you don't know the answer, it's probably 0.
I mean, you got like a 1 out of 3 chance. You got infinity negative.
I had an activity that we were going to do, but I don't think we're going to get there because you guys won't shut your mouths. If you have a question, ask it. If you don't have a question, be quiet. Stop complaining. Stop whining. Stop having side conversations. We have 0 times infinity. That is indeterminate. Does anybody have a question how we got the 0? Zero times infinity is indeterminate. But do we have a fraction? We have a product because it's 0 times infinity. If I want to make this look like a fraction, what could I do with this x? I'm really kind of stuck with the sign, but if I wanted to make a fraction, we can make it 1 over x in the denominator. Okay? If it's easier for you to see this way, this is x to the first power. If we move it across the fraction bar, it becomes x to the negative first power. That was unfortunate. Okay, so now what happens? 1 over x goes to 0. Sine of 0 is 0. Okay? X to the negative first is 1 over x. 1 over x towards infinity is 0. So now we have our fraction that we can use L'Hopital's rule with. Okay? It's the derivative of sine. So we have the cosine of 1 over x. The derivative of 1 over x, let's just call it x to the negative first, right? The derivative of x to the negative first is negative 1 x to the negative second, right? Because we have to perform the chain rule. The derivative of the denominator, negative 1 x to the negative second. What makes that nice? Okay. And now all we have to worry about, because remember you have to simplify before you try to plug anything in again. Now all we have to worry about is the cosine of 1 over x. Well, towards infinity, 1 over x is going to go to 0. So this goes to 0. And the cosine of 0 is 1. Everyone at your table is going to get a different problem. Okay? Feel free to help each other out. But I'm going to give you 2 minutes to complete this limit. I'm going to do it on the other part. You can. Yeah. Yeah, because you have expert and you have I didn't know if you guys your question answered. Yeah. Did you do it right? Okay. So just show me here like that was infinity over infinity so I understand that you did it again.
I think I did it.
What?
I think I did it.
It's not flowing for me.
Well, the natural log of 1 is
You did it to be 0, 0,
Okay, when you're actually given the value. When you're given the infinite, not that. No, yeah. That makes sense. You could.
It's literally just 3 times.
There's some that actually
So can't use process without it actually like precise again what they're doing.
So it's something that I think of those problems. You know, that should be something you get 6.
How you do that?
Okay.
You got it. Okay, good. Yeah. So then plug this in.
I shut my drive.
I still want to take all the drinks. Never use this.
It's just the
And like,
You get this one?
Okay, what I want you to do, if you have number 1, come to the door corner. If you have number 2, come by my desk. Number 3 by the flag. Number 4 by the couch. Okay, then you can compare with people who have your same problem.
Oh, we got the answers right. I got it.
yeah, but I was like,
I need my pencil.
Me too. Over here, do we have everything together? How to go over here? Okay, this is probably the toughest. Well, it's probably the toughest to do it if they use them out.
okay, how do you know that?
All right, back to your seat.
Yes, that'd be easier.
In the last 2 minutes of class, I want you to take your problem and explain to your pod how you got the answer. Okay, take turns.
So,